And with that, I am very happy to jump into the main session. So I hope you'll welcome Sean Derrington and Barak Epstein. They are two of our storage experts at Google, and they're going to talk about parallel file systems and object storage and how you can get great performance for your HPC and AI applications. Barak, Sean, thanks for joining us.
Great, thanks, Jay. Great to be here, and nice to see everybody online. A lot of some familiar faces and names. I'm Sean Derrington, as Jay said. Barak, my colleague, is joining, and we're going to run through a variety of things that are related to HPC and AI workloads. We have a lot of content, but we do actually want to save time for questions at the end. So we're going to do a little bit of an intro in terms of kind of how here at Google we've been looking at storage and how it applies to AI optimized infrastructure. We'll run through parallel file system as well as our cloud storage offerings, and then specifically we'll get into some of the capabilities, tips and tricks for training, checkpointing, and serving, and then we'll wrap it up and open it up for Q&A. So kicking things off, just to kind of understand a little bit of background about where we are coming from Google Cloud and thinking about AI. This is something that we've been doing for nearly a decade, and Forrester's actually recognized this as we're the clear leader in the AI infrastructure Forrester wave. You can see on the right-hand side, we're on the far right, almost all the way off of the chart itself. There are 17 of 19 evaluation criteria. We scored 5 out of 5. So I just want to kind of put that into context. I'm not going to spend a lot of time on this. This is obviously available for others online. But as I mentioned at the beginning, like this is something that we here in Google Cloud have been looking at for more than a decade in a variety of ways, whether it be in Gmail and Docs and so forth, and more, most recently, specifically for how companies can build their own infrastructure to train or provide inference capabilities around AI. And this is something you may have seen in previous sessions, and you will certainly continue to see this, and that is the concept of the AI hypercomputer, where this is our thinking, our organization about thinking about not only the infrastructure at the bottom across compute, storage, and networking, and clearly today we're going to be focusing on the storage aspect of that. But we also have other capabilities where we're looking at open software for different models like JAX and PyTorch and how you can optimize your inferencing, but then looking at managed services that we also offer around Vertex AI, and Jay mentioned a little bit of that. That'll be coming up on, I think it was June 24th. But then lastly, also on how you're actually going to consume this infrastructure. We've done a lot of work to make it easy to optimize costs where you know you're going to have planned spends, or where you need more of a dynamic and on-demand schedule. So depending upon how you know what your infrastructure is looking like, you can see at the top there, we do have flexible consumption models for compute and even storage in some cases. So I want to put that into context just because you're going to see that in multiple sessions throughout this series. But specifically thinking about storage, this is really a significant part of the AI data pipeline. There are a number of things that we've been spending time on over the last couple of years, understanding what I/O profiles look like for AI infrastructure, because it is quite different from traditional applications, whether it be databases or applications are running NFS, SMB, object, etc. That most specifically, if you think about how you're going to prepare your data, and Barak and I are going to focus on that middle section there between the training and inferencing, there are a lot of things that are going to basically go one of two ways: object storage or parallel file systems for any size, any significant size of a training model. If you're in the small range of a couple dozen systems, couple of dozen VMs and so forth, maybe an NFS system like FileStore or Google Cloud NetApp volumes would be fine. But we're going to be focusing more on the mid and larger scale, where you do have inferencing of hundreds or even tens of thousands of accelerators. We'll be talking about cloud storage, Fuse, as well as on the right-hand side, you can see the managed Lustre, which is the new offering that we have in the parallel file system space. I'm going to skip the details on here because we have much more coming up in just a moment. I mentioned that we spent the last couple of years really trying to understand what are the storage requirements for AI workloads. And really, these are kind of how we pared it down in the major things that we're trying to achieve. Number one, we really need to be able to solve an unlimited scale, whether it be terabytes to petabytes to even exabytes of data. You have to have a storage system that's capable to scale the capacity. But while you scale the capacity, you have to be able to meet the performance needs. And those performance needs come in the sense of not only throughput in terms of terabytes per second, but also how many requests are coming in, and the number of tokens that you're processing, the latency that's associated with that, and then also just the spiky nature of, if you're doing a training job and writing at a checkpoint, what does that do to your storage system? Does it actually pause an I/O to actually put the accelerators and lower the good put for the accelerators because they cannot sustain that throughput? Or how do you actually manage that if you're going to do trading and checkpointing at the same time so that you do maximize good put? So all of these considerations for storage are things that we've been inventing. And when I say that inventing, this is the things that we just announced at Next in terms of some of the storage innovations. You can see the long list here on the left-hand side are a number of cloud storage enhancements that we've been developing, as well as on the right-hand side, the parallel file system. Now, given the time that we have today, we're not going to focus on everything. So we did want to focus on more of the bigger impact. And there'll be some, I'll touch on like hierarchical namespace briefly, but to make a point here that we're going to spend the time this morning on some of the areas, just know that there are a lot of things that we are doing that we're not going to be covering in depth today. So with that, Barak, let me turn it over to you to talk about our PFS offerings.
Yeah, thanks, Sean. Thanks for teeing everything up. And yeah, great to see also a lot of familiar names and faces. So we're excited to be expanding what we're providing in the high performance parallel file system space. And if you've been following, you see that that's a space where Google's continued to invest over the last couple of years. And we have some recent announcements that I think are exciting and some pending ones. So, what drew us to parallel file systems? I think this will be familiar to many folks, but we have, an affinity to on-prem, that we have a lot of customers who come who have experience optimizing around a parallel file system and are interested to use that in the cloud. And, we've been obviously listening to our customers there. The workload profile, Sean talked about the I/O patterns that we've been seeing. This is an area where there's some gaps related to where our baseline portfolio was in terms of very high I/O, extreme high throughput, small files, and then saturating a single VM. So as we get to a situation where you have more expensive VMs with rising value and cost of GPUs, and then maybe mixed compute infrastructure. On the client side, there's more importance in being able to saturate a single VM, and so a parallel file system allows you to do that with a large corpus of data and directed towards specific client VMs. So the outcome there is, again, really about keeping accelerators saturated during training, high performance during checkpointing, and then there are some data loading benefits during serving as well. And what you see on the right is one sort of schematic that helps you to understand the sort of degree of improvement that we got over some of our traditional capabilities by moving to parallel file system. So specifically, at Next in April, just a month ago, we announced the allow listed GA of Google Managed Lustre. So many of you will be familiar with Lustre. We've worked very closely with DDN to develop a high performance POSIX file system. We're starting out with an aggregate of 1 terabyte per second read throughput on a petabyte scale. And those are numbers that you should expect to see increase. That's a very high priority for us. You have sub-millisecond latency and millions of IOPS, and it's a persistent storage. So some integrations we've worked on include CSI driver for GKE deployments. I'll talk a little bit more about that later, and cloud storage bulk transfer API. We're going up to thousands of VMs. And there's full duplex performance for training, checkpointing, and inference. So we do have customers who will maybe see more of a performance benefit on either training or on checkpointing, but then decide to centralize their storage footprint on a single parallel file system. So it's just a little more detail on the current offering. So it's available now. We are for a little while under allow listed GA, but that'll be planned to be removed shortly. And we have one tier, but as noted, as you look at the glance ahead to the future areas of focus, that is an area where we expect to have some announcements soon. So right now you get 1 gigabyte per second per terabyte for reads. So that's where you get that's just the math that will drive the terabyte per second aggregate. 4,000 client connections and up to 6,000 GPUs at the moment. We have you can go as small as 18 terabytes up to 1 petabyte. We have the GKE CSI driver, Terraform, and then cluster toolkit. And those modules are available online now for Lustre to help automate and orchestrate your deployment. 99.9% SLA. And we do have some enterprise features around directory quotas. And then future areas of focus include, as I mentioned, additional performance levels, additional data management investments. So right now we have a bulk transport API, but there's some extensions to that'll make data movement easier, and then just continuing to invest in security and compliance. You see the initial regional availability on the right. So just a few words on the managed Lustre GKE integration. So basically, if you're familiar with GKE and using persistent volume claims, then most of this will not be news. But for those newer to GKE, there is a little bit of back-end work to make a storage system work seamlessly with it. And so we've done that work so that Lustre can be better set up with GKE admins. And you may have this in your own organization. You might be someone who doesn't come from a storage infrastructure background yourself. And obviously we're seeing more of that as over the past years, but especially as AI ML takes off. So this helps to make the GKE more of your front pane for integration. So right now the CSI driver is unmanaged, but that should be corrected shortly, improved, and so that that's one area where we're excited to continue to invest. We also have batch data transfer. So we basically have internal capabilities around and sometimes externally surfaced. You might be familiar with our storage transfer service, for example, but we've integrated this into the API for easier programmability. So customers can transfer data between cloud storage and managed Lustre. And so there are a couple of main reasons, I suppose. So one is just having a single landing zone for your data becomes easier to be adaptable and agile. Secondly, to the extent that you can make intelligent decisions about where to place the data on a higher or lower performance tier, there's a cost blending benefit. So we've also invested in this data transfer speeds, in optimizing transfer of small files. And so that's going to continue to be an area where we focus, because we do think this pattern is going to be, continue to grow. And we are seeing more and more customers move this direction. So just to summarize sort of the value proposition here. So consistent performance for single, few, or thousands of nodes. So you can expand your number of clients and expect to see, similar performance. The per VM throughput, which I talked about in a little more detail earlier about saturating a single VM, and then centralized use of storage for multiple use cases. So we'll talk about that more later, but from a different perspective. But the idea that I don't want to worry about storage and I want it to work for a wide variety of use cases or a wide variety of file types, that would be part of the value proposition. And we talked about the Google Cloud Storage integration earlier, but obviously saving checkpoints, they can initially be saved to manage Lustre and then move back to cloud storage for long-term storage. Perfect point to say back to you, Sean.
Yeah, thanks, Barak. Yeah, as we look at the offering there, right, the parallel file system does present a file system to your clients. And so one of the things that we've invested in is making object storage look like a file system. And one of those ways is to support Fuse. And we've done this for many years, so it's not new. However, what is new is that now it's a Google supported and Google managed offering. So for those that may not be familiar with this, This allows you to mount an object storage bucket as if it was a file system. And so what that means is you don't have to rewrite your AI workloads. If you're moving from on-premises coming to the cloud, you may be able to use this fairly seamlessly and more of a lift and get ready to train as opposed to spend time re-architecting. And what that does is it allows you to reduce those resources. All right. So if you have a file system like interface, you can potentially drive better throughput. And there's some things that you see in the workload performance optimization area here that I'll talk about in just a minute. But I did want to point out that whether you're using PyTorch or TensorFlow, you can basically think of a bucket now as a file system. It's not a true file system, so there are some caveats, but for the most part, it does behave like a file system. And what that does is it actually lets you think about how you want to organize that data. Barak mentioned some of the cost optimization things that you can think about. So the first question is for a regional bucket, you have the option to say, okay, I'm going to have my bucket in one region. Dual region begins to, obviously, the name implies, have that replicated across two regions, and a multi-region distributes that data across multiple regions within a continent that we decide where the capacity availability is, but it makes it very seamless. Now, one of the unique things about cloud storage is that regardless of if it's a regional, dual region, or multi-region bucket, you still have a single bucket namespace. So you can think about continental scale buckets regardless of which type of region you choose, in addition to the storage classes below that. The highest performing is going to be standard on the left, as you expect. That's also going to be the more expensive storage class. And as you move to the right, the cost decreases. However, there are considerations between how long that data is going to live in a given bucket, if they're going to be class A or B operations, and if they're early deletion fees, et cetera. If you write out to archive, you have to have it there for a year before you incur a deletion fee. The other consistent thing that you'll see here, in addition to that single bucket namespace, is relatively consistent latency from all those storage classes. And this is a differentiation against other cloud storage considerations. So as you think about your bucket location, this is the first construct as you need to think about single, dual, or multi-region buckets. And that's really where you can begin to leverage anywhere cache. So as you think about a bucket, you can enable anywhere cache today on any existing bucket. So it just works literally in a single command line or API call, or even a Cloud Console click. You can enable anywhere cache. As the name implies, this is a read cache that you can now specify a specific zone within a given region to cache data up to a PIB of capacity, up to 2.5 terabytes of throughput for performance. But it also is very efficient and optimized, where you'll be able to see in the observability what those cache hit rates are. And you don't have to specify exactly how much, but you can just enable this, and you'll have a predictor to tell you a little about what that characterization and what benefit anywhere cache could deliver. Now, you'll notice there that in the diagram, there are 3 different regions with 3 different zones, one in each region. This is the idea of, you'll hear this consistently throughout what Barak and I will talk about in terms of keeping the data close to the accelerators, finding out what zone you have accelerators available in, getting either the training data, or in this case could be training data or inference, and making sure that that is as close as possible to maximize goodput. You'll also notice that below those 3 regions, I indicated a multi-region bucket. This is a significant advantage that allows you to decrease your costs by not paying egress fees within a continent for anywhere cache or other data access needs. And so that's one of the advantages of a multi-region bucket, is to be able to provide you with the ability to move and optimize where that data is placed closest to the accelerators. The other thing that anywhere cache does is it dramatically reduces the latency. As I mentioned, you can have up to 2.5 terabytes per second of throughput. And that's a significant thing to think about in terms of QPS or bandwidth allocation. And what it does is you'll actually see up to a 70% reduction compared to a regional bucket. So that top metric there is combining anywhere cache with a multi-region bucket compared to anywhere cache with a regional bucket. And what that does is you can see the cache hit ratio. I took a screenshot there of the observability, and this is one of the things that you can see, and obviously it's going to have a significant impact on training results. And if you go back to what Barak showed at the beginning with the parallel file system, where you want those epochs to be as short as possible so you can continue right out the checkpoint, move to the next epoch. This is one of the things that's going to significantly help that performance from a training perspective. And we have a number of customers that are using this. Obviously, you can recognize some of the big ones like AI. Spotify's done this really to focus on their egress costs. So while not specifically around AI, although they are doing a lot of things around AI, they, as you imagine, they are looking at data distribution and caching data in multiple regions for listeners, and this is one of the ways that they've done that. And they've also used auto class within cloud storage to decrease their costs significantly. Two Sigma's a financial organization that is doing AI workloads, and you can see that they're able to scale and use Anywhere Cache to support their compute scale. The last thing I'll mention about Anywhere Cache is that this is something that some of our more advanced and sophisticated customers have done over the years because before we offered this, but you can think of this as really the easy button. You can build your own cache, you can spin up your own VMs and try to do this, but this is one of the things that just works with any bucket that you choose for not only AI workloads, but other AI workloads, for example, analytics and other things. But obviously this morning, we're focusing on AI and HPC. I mentioned about keeping the data as close to as possible to your accelerators. And so Managed Lustre is a zonal offering. Barak mentioned the 4.9 availability there. This is a zonal offering that keeps the data close to accelerators. Well, what if you can create a bucket that is also a zonal offering? So this is a new offering that we announced at Next called Rapid Storage. This is in preview. And this is, again, as you can see here in the blue, it's a different consideration. It is not a regional bucket. You can populate this zonal bucket called Rapid Storage with a subset of the data in other buckets, but you have, again, that idea to be able to take a subset of the data, get it close to accelerators, and either do training and or inference. The thing with Rapid Storage is that we've also thought about how do you continue to make a file system like interface to an object storage bucket. And so Fuse works with Rapid Storage to provide that file system interface. But what I wanted to point out here that Rapid Storage is actually built a little bit differently than the other buckets. And so this is going to give different performance characteristics, which I'll talk about in just a second, but this is actually built on Colossus. And you can go, we actually put out a couple blogs around Next regarding Colossus and what that actually enables us to do to deliver very high performance with HDD as well as SSDs underneath the covers. But specifically around Rapid Storage, what this does is it allows us to integrate with Colossus and basically create via the gRPC API communication that essentially eliminates a lot of that intermediary communication and latency that can slow down overall performance for a typical storage bucket. And so as we continue to look at the storage needs for AI workloads, we're going to continue to improve how object storage can be used for AI, as well as how PFS solutions can be used for AI workloads. So you can think about this really as trying to have an object storage bucket behave more like a file system, or maybe like a parallel file system, particularly around latency. You'll see there in the lower right there, the built-in the directory support for hierarchical namespace. This is important because one of the things that can impact the training latency, whether you're writing on a checkpoint, is actually, and the I/O patterns I mentioned before, is if you want to update an individual file, and you can actually begin to do things like get append with Rapid Storage. If you're going to rename or you're going to walk a file system tree, it takes a long time in a flat namespace. But if you introduce and continue this concept of making an object bucket look like a file system with HNS or hierarchical namespace, you can dramatically improve the performance for that. And one of the things that we actually have done to improve the performance for storage is with Rapid Storage, I mentioned eliminating that a lot of those intermediary communications with the gRPC API. This allows us to actually deliver less than a millisecond latency. And yes, you are reading that correctly, less than a millisecond latency for files. Now, this is after the file is open, but once that file is open on the client, once that client has that file loaded and open, you can now iterate and have varying I/O patterns access that data in very low latency. So no longer are you talking in tens of milliseconds in a traditional regional bucket, but rather you're looking at, you see here on the charts here for the P50 appends and random reads, sub-millisecond. Now that's also 5 times faster than the other leading hyperscaler that has a zonal offering as well. And comparing to the standard regional class, which I was mentioning, that's 20 times faster. So as you think about this, you can begin to think about, well, maybe a cloud storage bucket will be the right way to go. I mentioned this is in preview. This will be GA later this year, so stay tuned with that. If you're interested in using that, we can certainly give you access to that, and you can begin to look at that. But again, similar to like Anywhere Cache, this is not strictly focused only on AI and HPC workloads, but today's topic it is. But if you have other high performance needs for cloud storage, that is definitely a consideration. So with that, let's transition to some of the specifics and tips and tricks I mentioned at the beginning of the call around training and checkpointing. Barak?
Yeah, thanks, Sean. Yeah, so you can see that we've been trying to optimize storage across many dimensions and many different products. And we have one slide here just to give you a sense of where we start seeing some new patterns and varying patterns, especially specifically starting here in the training space. And maybe that'll sort of suggest to you where different types of storage would be useful. And I'll have some comments on that. But obviously there's a continued consultation that can happen. So we do see in some training that we have what we're calling file parallel plus sequential. So this is excellent. You can have large data sets that have sort of predictable IO patterns, and that'll tend to be a sort of less finicky storage pattern. You may have more latitude in terms of which solution you choose. Sometimes there is a file parallel, but then random within a specific file. So this is a little bit of let's call it a gray zone, where you may see that GCS is great for you, or you may start to see that the random reads make a parallel file system more attractive. And then we've done some optimizations that we'll talk about as we go through in terms of making really either solution work well for this type of pattern. You could have a fully random pattern. I think that's mostly self-explanatory, but the file is sort of let's just call it irrelevant to the pattern, and that you're reaching across different patterns. And then you can have multimodal, where you start to have training sets that may have some combination of these patterns. As a PFS product manager, I tend to see that as like a great reason to go to PFS, but your mileage may vary. But if you think about the one-stop shop there and just being able to be flexible in terms of training, that is a design consideration that you may take into account as you develop your infrastructure. Here we have a testimonial from Assembly AI, which does enterprise grade speech AI. So they process petabytes of audio each year, and over 7 billion inference calls. So audio files, it's been interesting space for us to go into, and you end up seeing slightly different patterns, moderate size files, and then a variety of different sort of training patterns depending on specifically what type of output and what type of training the customer is going through. But they basically, based on our optimizations in cloud storage, the customer observed a 10-time increase in throughput and a 15x performance improvement. So there's quite a lot of work that can be done and that has been done. Sean will cover some more of that, but we start talking about using GCS views, which gives a file adapter to cloud storage, and then hierarchical namespace. Those are some critical elements in this particular case. Another area we've invested is parallel downloads that have helped to optimize some of the training patterns for GCS views. Just going back to moving on to checkpoints and going back to managed Lustre. So, I've referenced a few times how the duplex nature of the reads and writes can, suggest that you may want to have a checkpointing and training on the same storage medium. And then, you start to pay attention to other set of patterns to keep in mind would be, is the checkpoint distributed or centralized? Is it asynchronous or synchronous? This is another area where parallel file systems are more flexible. If you have specific patterns, they may align really well to Google Cloud Storage as well. And then, just referencing again the import-export API. I'll just add in a quick little plug, as we, hopefully be talking to many of you in greater detail, but just want to focus on the fact that we have been doing quite a lot of benchmarking work across these different storage media, across different AI, ML patterns, and really developing a lot of insights and continuing to work to publish those and help customers benefit from those. So with that, I'm going to pass back to Sean to dig a little deeper on the checkpointing with GCS views. Yep.
Thanks, Barak. And one of the things to keep in mind with particularly with the checkpointing with Lustre is that because it's a persistent offering, you can actually have the training data and the checkpoint in the same file system in the same instance. You don't have to think about things a little bit differently. And I'll contrast that with GCS and cloud storage in just a second. But the other thing that I want to point out on that previous slide was the very high throughput. You notice that that Lustre can actually saturate a VM at 20 gigabytes per second. That's very important for checkpoints so that it can continue the training and it's not impacting that training workload. And so one of the things that we've done with Fuse and hierarchical namespace again is giving the ability to actually improve the frequency of checkpoints that you can write because we've been able to improve how much faster a checkpoint can complete. Particularly thinking about how quickly the whole software layer, the Jackson TensorFlow and everything, and the AI workloads are changing between synchronous versus asynchronous checkpoints. That asynchronous checkpoint allows the system to continue to process. But if you look at sometimes checkpointing in a cloud storage bucket will actually require an atomic folder rename. And in a flat namespace, that takes a long time. And if you look at the chart here, you can see in the flat bucket, the gray bar, that's one of the things that's just it's a function of an object storage bucket, right? And so one of the reasons that we added and created an HNS option that you can use for your bucket is it allows those atomic renames to be very isolated and much more frequent. And so you can actually do this to a specific folder, and that decreases the time that it takes a checkpoint significantly. You can also see in that last bullet there up to 8x of higher initial QPS for read and write operations. That's important. So as you think about the streaming writes, you can actually begin to think about how you can do a full file stage and complete that 40% faster with the other path. And if you look at the bottom there, you can see the amount of time that it takes for an HNS bucket to write a checkpoint versus the flat, where you see the long drawn out. And again, this is all about improving good put and maximizing your TCO by spending the money wisely on accelerators. And in cloud storage, the other thing to think about for checkpoints, I mentioned that with a parallel file system, you can have the training data and checkpoints in the same instance, and that's not going to be an issue. With cloud storage, you have to be more cognizant of that. And one of the recommendations is to actually write out your checkpoints to a separate bucket than your training data resides in. Now, even though you're writing out to a separate bucket, you do also want to make sure that the bucket is in the same region that the accelerators are. So you don't want to write your training data in Central 1 and then your checkpoints out to South 1 as an example, because obviously you're going to have latency if you're going to try to do any writes, but more importantly, perhaps any resource is going to take an extended period of time. I mentioned asynchronous checkpoints. This is one of the things that you want to enable wherever possible to accelerate that performance. But then the other thing in terms of optimizing the costs for checkpoints is to actually think about two things. One is soft delete, which is basically an undo button that allows you to define a period of time that if you do delete a checkpoint, it's actually reserved in cloud storage for N number of days that you define, so that you can go back and basically undo and recover that file even though you've deleted it. Auto class I mentioned before is a way that Spotify has saved 37% of their costs for storage. This is the easy button for tiering storage. So this will initially write it out to standard storage class, and then based upon a predetermined policy, migrate that down all the way to auto class, migrate it down all the way to the archive storage class, which is significantly less expensive than standard. So enable soft delete and archive and auto class, for that. The other thing that we're doing to accelerate checkpoints is a multi-tier checkpoint. So this is different than the traditional checkpoints we've been speaking about. This actually writes to in memory first. And so in your GKE cluster, we will actually take the checkpoint and write that to the memory of the cluster, but they will also replicate that among multiple nodes within the cluster for durability, but then eventually you can see also externalize that out to your cloud storage bucket. So this is one of the things that you have to think about a little bit differently in terms of where your recovery points are and how many times you're going to be taking checkpoints. Particularly for large clusters, this is one of the things that allows you to take a checkpoint in a very small amount of time. It takes about 10 seconds for writes, and you can actually scale this up to about 1,000 nodes so far within a GKE cluster, and that's just kind of what we've been testing. This is in preview right now for JAX and TPUs. But the thing I want to call out on the slide here is that 6% good put improvement in red there. And this is one of the most expensive parts of your AI infrastructure. And so as you've heard Barak and I talk about this throughout the session here, it's all about maximizing that goodbit, because a little bit of time saved is actually going to have a significant impact on your overall TCO. And so a quick solution here, just kind of a comparative of where on cloud storage on the left-hand side, where you can take checkpoints every 5 to 10 minute frequency, just based upon the amount of time that it takes to write them out. You can actually use, and again, our recommendation with hierarchical namespace, as well as streaming rights. You can see in the middle, PFS, very, very high performance checkpoints, not only writes, but also reads. And on the far right is a multi-tier checkpointing. So things to consider, again, based upon your architecture. If you're writing for the very first time and architecting for object storage, you have some different options. But if you're looking at PFS, that's also something to consider. The last thing that we wanted to touch on before taking some questions is serving. This is one of the things I think we'll see more and more people focusing on, is how do they actually do inferencing or serving. The way to think about this from our analysis over the last couple of years is really to focus on the GPU and TPU utilization. If you're going to spend a little bit more on storage to make your utilization of your accelerators increase, that's going to be a bigger impact to the TCO savings than trying to pay less for storage and have your accelerators sitting idle. It also depends upon the model frequency and size of what your updates are. So Cloud Storage Fuse is one of the things that we've done. We've added parallel downloads that allow you to do inferencing at a very high performance. So this is actually one of the things you'll see for a Llama B70. We've actually improved the performance of inference by 9x with parallel downloads. I mentioned Anywhere Cache at the top of the call here for training, but also inference. This is one of the things that, again, allows you to deliver very high throughput to a specific zone within a continent that you can define based upon availability of accelerators from day 1 to 6 months from now, if they're not in the same place. The other thing to think about for inferencing is to think about the multi-region bucket as kind of the default. Again, that gives a lot of flexibility with Anywhere Cache. Although if you want to choose 2 regions for dual region redundancy, that's also definitely an option. And then also on the managed Lustre side, so if you're using managed Lustre for training and you're doing inference out of the same zone, it makes a lot of sense to use that for inference as well. It has very high performance to a few VMs or a lot of VMs, depending upon how many VMs you're serving out of. And that's a contrast to cloud storage, which really works with lots of clients in parallel very well. But if you need very high performance to a few VMs, that's where Lustre is going to have the advantage to saturate that 20 gig length. If you're not using Lustre for training and you have a need to have very high performance inferencing, this might be where you would spend the extra money on storage to do inferencing faster and, again, save on those accelerator costs to improve your TCO. The last thing I wanted to mention on inference is our block storage offering. So Barak and I have been talking really about our file offering. And when I talk about file on object as well as PFS, but Hyperdisk ML is a block storage offering. This is unique, again, mostly for inferencing, where you can now attach an HTML volume, HDML volume, not HTML, but an HDML volume to up to 2,500 VMs. And obviously that's important for scaling out inference capability. But you'll notice there that it also delivers very high performance, very high throughput of 1.2 terabytes a second. And that's very advantageous because you can deliver that throughput and you can size the capacity of your HDML volume at a couple hundred gig to a terabyte and still deliver very high throughput of that 1.2 terabytes per second. There's you have to pay for the additional throughput, but it gives you that opportunity for smaller volumes to deliver very high performance. You'll notice there that this actually delivers up to 4 gigabytes per second per VM, so a little bit different than PFS at 20. But it is one of the things that you can still do very high performance inferencing compared to cloud storage typically, just as you can with PFS. Again, depending upon the frequency of which your models are being updated, this is one of the things to keep in mind because HDML is a write once volume and read only after that. So after you have a new model, you have to create a new volume with those new models that you're going to be serving up to the VMs. So it's a little bit of a process change as opposed to if you're using PFS, you can just update the file system and it's just in place update. So keep that in mind with a little bit of a process change, but it is one area where you can deliver very high performance, again, to maximize the accelerators. So as I think about this, really two things to think about for AI workloads in Google Cloud. Object storage and parallel file systems are the two recommendations. Depending upon where you're coming from, PFS will oftentimes be the first step. But if you're writing coming from an object space, clearly we're doing a lot of things to make object storage behave and perform like a high performance file system. But one of the things that we've been focusing on is, what do you do with this? Right? So one of the things is that we are building a storage infrastructure, and today we focus on storage, but I'll refer you back to the AI hypercomputer for the networking and compute things that we're doing as well for the hardware infrastructure to really focus on how you can accelerate your AI and ML workloads. We are innovating very rapidly in the cloud storage space, specifically around rapid storage and anywhere cache, hierarchical namespaces. Those are all new this year. Rapid storage will be GA towards the end of the year, but we're also continuing to invest in our parallel file system offering with Lustre. And Barak gave a little bit of a teaser about where we are today, but as you can imagine, we are going to be iterating very quickly on feature enhancements across the board for the managed Lustre offering. So with that, Jay, let me turn it over to you and see what questions we have from the Q&A panel.
Great. Thanks, guys. It was a fantastic presentation. Love that overview and the comparative positioning of those two solutions. So we have some great questions as well that will expand the conversation. I'm gonna give you the softball question first from Alex Chekholko. So this managed Lustre is distinct from the file store offering, correct?
It is. Those are two different things. File store is an NFS offering, which is also a Google managed service, but it is because of NFS, we do have limitations on the protocol. And so you think about parallel file systems differently, and then it can behave and perform deliver very high performance to a few VMs or up to thousands of VMs, right? This is one of the things that file store, we've done a lot of work, and we do have customers that are using file store for AI workloads. Salesforce is one of them, for an example. And it's really well suited for kind of a couple dozen VMs, but it's not going to scale to the hundreds or thousands or even 10,000s of VMs, just because of the nature of NFS compared to PFS.
Great. Next question is from Alexander Bauman. He said, do you have info on the times it takes to create a new Lustre file system and transfer from a bucket to there and the other way around? Specifically in the cases of shifting from cloud storage to high performance storage temporarily. So any info on the time it takes to create and shift?
Yeah, so the creation is in the tens of minutes, which is, to be really frank, not where we want it to be, and we're planning to bring that down. But depending on the size of the instance, 15 to 60 minutes is where it is right now. The transfer, 100 gigabytes a second. So if you had a full petabyte, you may have 18 terabytes, and then that'll be much less time. But a full petabyte would take a little bit under 3 hours. Now, the only mileage vary element there is just if you have lots and lots of small files. So that can still be a bottleneck, but that's very typical.
Thanks, Barak. I have another great question from Alexander, so I'm going to ask it now. Can you talk quickly about some use cases for the fast zonal bucket storage versus just copying to an SSD PD? The example it showed had the bucket mounted using Fuse, so it seemed like it was being used as though it was a POSIX file system anyway.
Yeah, so a couple of things. One is that if you are going to use Fuse with your cloud storage bucket, it is not going to be POSIX compliant. That's number one. So things like multi-writer aren't going to apply. So you have to think about that a little bit differently. If you're writing it to rapid storage, it's going to have the characteristics that we've been talking about with anywhere cache, the option for in the future with HNS and things like that. If you're writing it out to a persistent SSD, you're then going to have to create your own file system and manage that separately. So it's typically not a workflow. I mean, we have seen that if you're doing like HDFS or things like that, we have seen that. But I would think of those two things as different approaches and lean more towards kind of the rapid storage and keeping things within cloud storage because of the ability to move between GCS buckets much more easily, or PFS is another option, right? Depending on performance needs.
Great. And I have a question from Mohsin Sheikh related to performance of PSF. What sort of tools are in GCP to observe the PSF performance to analyze I/O profile of an application?
Yeah, so we have cloud monitoring, which will be rolling out with the full OpenGA, and that'll support monitor client metrics on read-write bandwidth, IOPS, latency, and number of clients. So familiarize yourself with the cloud monitoring tools, and we'll have further documentation on that as well.
Great. Going back to file store just for a second, Sean Reddig asked, is there any reason to use file store over managed Lustre or GCS views with hierarchical namespaces?
Go ahead, Brock. Go ahead, Brock.
Yeah. I think it's hard to summarize in a quick sentence or two, but there are a lot of enterprise features on file store. So if you have an NFS application, you have a sensitivity to particular enterprise features. It's had more time to mature on Google Cloud, and then you don't think you'll hit one of the bottlenecks that we've referenced. And there are a number of them, and that's why we built these alternatives. Then definitely file store is something we're really proud to be sharing. Yeah.
Yeah, I'll add one other thing. It's you can think of file store as the easy button for small scale training or inferencing. If file store is integrated with GKE, so the CSI driver Barak talked about is available for a file store. It performs well. It's up to file store zonal is up to 26 gigabytes per second at a full 100 terabyte provision capacity. So that's another consideration, is that it does have a volume cap at 100 terabytes versus a petabyte for PFS for Lustre, or unlimited for cloud storage. The other thing that Barak mentioned was the performance. File store behaves similarly with cloud storage to a few clients, so you're not going to be able to deliver very high throughput to only a few VMs. Unlike PFS, where it could be with Lustre, it can write very high performance to a few or thousands.
Great. And another comparative question, this one just in from Yi Chen. How do you position managed Lustre along with parallel store?
Great question. So there are a few. Managed Lustre, I think will hit the broadest range of use cases. There are some cases where parallel store could be interesting to you. So it's a scratch offering, which means it's not fully durable. It also means it can be more cost effective. So if you're very sensitive there, that's an option. Also, in cases with very extreme IOPS, there are some better characteristics there. Not typically something we're hitting in AI ML training lines, but in some HPC use cases that this community be familiar with, that can be a factor. We do have parallel store. We also have a range of partner solutions that may match your needs as well. So we definitely encourage you to look across our portfolio, and we're emphasizing where our investment's been in our focus in recent months. But please look at what we're doing as well with, for instance, with GPFS and our partners. So yeah.
Great answers to these questions. Questions are still coming in, and we're running out of time. I have a few really important announcements to make next. So I'm going to ask the folks online whose questions didn't get answered to this week email them to gcacc@google.com. It's GCACC, Google Cloud Advanced Computing Community, at google.com, and I will forward them to the speakers and we'll get you answers. By the next session in 2 weeks, we will have an online forum in which you can ask questions after and between sessions, so we can get more questions answered to our growing community.